Dear students, welcome back to online classes. Today we'll see Ampere Circuital Law. So before going to this Ampere Circuital Law, briefly we'll discuss about Gauss Law in electrostatic, and we'll discuss about electric flux. So what is the electric flux here? The total electric flux through a surface in an electric field is defined as the surface integral of electric field over the that surface. It means this is a one circular loop. I will consider this is the surface, small surface of this circular loop, and then from this surface how many number of the electric lines or a electric field is passing through this surface, that is called as electric flux or electric intensity, electric flux. So here what the Gauss law is explains. So the Gauss law is, or a Gauss theorem is explain the total electric flux through the this surface, total electric flux through this surface, or any closed surface. It is called as a, this is a closed surface in a free space, is equals to the 1 by epsilon 1 by epsilon naught times, it is equals to the, in a free space, 1 by epsilon naught times the total charge enclosed by the surface, the total charge enclosed by this surface. So that is gives the Gauss law. So we got a expression from this Gauss theorem, that is closed integral of electric field into a ds. ds is a small surface area, is equals to the, q divided by epsilon naught. So this is the expression of Gauss theorem or a Gauss law. So this theorem is related whatever we are going to study in this session. So that is Ampere Circuital law. And also we come to know that already we have studied one of the expression, that is Biot-Savart's law expression, and we have derived that expression also. For that Biot-Savart's law we have used a one conductor. For that conductor we are supplying some current, small current. So due to the that current, what will happen when it is moving through that current, the surrounding of that conductor, the magnetic field is generated, and at every point what the magnetic field is produces, we have calculated by using the B equals to mu naught divided by mu naught I divided by 2 pi r, or you may take any one of the constant of a or r, or otherwise you may take x. So this expression we got. So from this expression we will calculate the magnetic field which is generated by the conductor. So if I closed this circuit, if I closed this circuit, so then what the magnetic field is going to be generated, will study by using the Ampere's circuital law. Now we will see the statement of Ampere's circuital law. The statement is that the line integral of magnetic field, is the product of the sum of current and permeability of free space, So therefore here the line integral of, or it may be called as closed integral, the line integral of magnetic field into a small current element dl is equals to the the permeability mu naught into I. So we have taken here summation of I. Why? Because this is the conductor which is having the diameter or a radius r. So at every point of this r, I will take larger one of the conductor here. So this is the central axis of that conductor. If we consider this is the radius of r, if you are going to find the magnetic field at this point is a different, and at this point the current is also flowing through this one is a different. So that's why we are taking as summation of I. If you are going to calculate to the complete of this conductor how much current is flowing through it, so that is gives the that summation, otherwise sum of that algebraic of current. And now here what we are going to do, I am considering from this conductor, this is the one of the conductor. In this conductor I am taking a one loop or one area of that conductor. At this point what the magnetic field is going to be produces. If we see in that one, let us will consider this is the one closed loop. In the we will consider this is the conductor. So in this conductor I will consider the this is the closed loop. In this surface, in a closed surface, so what the current is flowing, I2, I3, I4, I5. So these currents are flowing, but the current is in a different direction. So how will you calculate that one? This is the summation of, it means we'll take I2 plus I3 and minus of I4 and minus of I5. So this is gives the current which is flowing through the that conductor. So now what we are going to calculate, so we are going to calculate the magnetic field for the that closed loop. So B is indicated the magnetic field and dl is a small current element, and which is we are taking at this portion. So that is gives the small current element, and mu naught is absolute permeability of free space and I is current. So this is the statement of Ampere Circuital law. So now what we'll do, we will derive the expression, or it is called as proof. So now let us consider what we'll do here. First we will see the Biot-Savart's law. Savart's law, the magnetic field due to this current carrying infinite conductor at a distance or a r distance is given by the Biot-Savart's law, that is B equals to mu naught divided by 4 pi 2I divided by A. So to get cancelled, then we will get the mu naught I divided by 2 pi A or 2 pi R. Any one of you take, that is A, otherwise R or X. Now what we'll do here, we'll do the proof of this Ampere's law by using this Biot-Savart's law, or we may use the that statement of the Ampere's law and then we'll prove the this Biot-Savart's law equation. So now here let us will consider one of the straight conductor, infinite straight conductor. This is the infinite straight conductor which is carrying a current I. So what will happen if you are using the Biot-Savart's law? Then I will take here at the point of P. At this point of P, what the magnetic field is generates or produces when the current is flowing through the this conductor. So I will draw the magnetic field line here. This is the magnetic field line. This is the magnetic field that is in circular loop which is produced by the that current carrying conductor. So now what we'll consider here, we'll draw neatly this one. Now we'll draw a one of the Ampere circuital loop. See here, I will take a different color here. Ampere circuital loop which is overlap on the magnetic field. This is the Ampere circuital loop which is over the magnetic field loop. So now this Ampere circuital loop and then this magnetic field line both are in the same direction, both are in the same direction, then the angle between the this Ampere circuital loop and magnetic field both are the same, so therefore the angle between the that loop is 0 degree. So therefore now we'll derive that equation which is we are using in the Ampere circuital law, that is nothing but, now this is the closed loop, so therefore closed integral, closed integral, the product of, or a line integral, the product of b dot of dl, b dot of dl, we are considering this current element here. This is the current element. For this current element, what the magnetic field is there, that is the b dot dl is equals to the mu naught into the current, mu naught into a current. So now this dot product we can write, this dot product we can write closed integral of b into dl into dl cos of theta is equals to the mu naught I, equals to the mu naught I. Now we know that theta equals to 0 degree. So therefore the line integral of b dot dl cos of 0 is equals to the mu naught into I. Mu naught into I. Therefore now here, therefore now the equation becomes, okay, we will take this, b is a constant, so we'll take outside, and integral of dl cos is 0 is 1, then the equation becomes mu naught I equals to the mu naught I. So what is the dl? So dl is nothing but circumference of the circle, circumference of the circle, dl is the circumference of the circle. So therefore the circumference of the circle is this is the distance between the center of the that conductor to the point which is we are going to take the magnetic field. So that is gives integral of dl is equals to the line integral of dl is equals to the 2 pi a, 2 pi a. Now the equation becomes b equals to the equation becomes b is equals to the, sorry, we'll write here, into 2 pi a is equals to the mu naught divided by mu naught into I, then the magnetic field of straight conductor which is gives to the Ampere circuital law, that is mu naught I divided by 2 pi a. This is the proof from the that Ampere circuital law. So this is the very easiest way to find the magnetic field for a straight conductor, infinite state conductor. And we have find this expression in a Biot-Savart's law also, and here also both are the same value is given, but only the thing is different, the derivation is complicated in a Gauss law, and it is a very easiest method in the Ampere Circuital law. So here we'll get two cases. There are two cases. First case is that case first. So we'll write this case, or otherwise first we'll write this is the proof of Ampere Circuital law. So if you go reverse from this equation, then you will get that equation, that is b dot dl, integral of b dot dl is equals to the mu naught I. Both are the same, so both will gives the same equation, that is Ampere circuit law only. And in this Ampere circuit law we'll see two cases. Consider one of the conductor. I will take here one of the conductor. So we'll draw one. This is an infinite conductor. We'll draw a central axis of that conductor. And now here there are two cases. One is what the magnetic field is inside the conductor, and another one is there what is the magnetic field outside the conductor. So first we'll see what is the magnetic field outside the conductor by using the Ampere Circuital law. So this is the magnetic field point, this is the magnetic field point, and over this magnetic field point, over this magnetic field or magnetic loop, will draw a Ampere's loop, and this both will parallel to each other. It means the angle of the angle between the magnetic field and the Ampere loop of dl is 0 degree. So already we have explained above. And now what we'll do here, this is the, we'll take r, this is the distance r, and first we will take here, this is the distance from the axis of the data conductor to the end of the conductor, that is a, we will consider. And now here the r is, in this case the r is greater than of a. First we are finding that is outside the conductor, outside the conductor. It is not necessary, but we should know what the magnetic field will get, and then how will get, if it is increasing or decreasing at the outside the conductor and inside the conductor. The magnetic field is in or decreasing or increasing. So here in this case the r is greater than a. By using the Ampere Circuital law, so that expression is line integral of b dot dl, line integral of b dot dl is equals to the mu naught into I, summation I you may take, otherwise mu naught into I. Already we have told the dot product we can write integral of b dot dl into cos of 0. We know that the angle is 0, so therefore the equation becomes like this. And now b is a constant, so dl is nothing but 2 pi r, 2 pi r. Otherwise we'll write properly here, b integral of dl is equals to the mu naught I, and the dl integral, closed integral of dl is equals to the 2 pi r. So from this point to this point, so 2 pi r. And now here we'll put the value of dl, that is b into 2 pi r is equals to the mu naught divided by I, sorry, mu naught into I. Therefore the magnetic field at this point the magnetic field at this point, that is B equals to the mu naught I divided by 2 pi into R, where it is outside that conductor, and which is drawn a loop on that magnetic field. And here the magnetic field is inversely proportional to the distance. Magnetic field is directly proportional to the I, but inversely proportional to the, that is, distance. So this is the expression for the magnetic field for outside the conductor. And now we'll see the inside the second case, that is inside the conductor, what the magnetic field is going to be produced. Here also we'll consider the infinite conductor, and in this conductor we'll consider one of the Ampere loop. This is the Ampere loop we'll consider, and the Ampere loop of the radius is R, that the radius is R we have taken. And here the current, already I have explained that by using these while explaining the Ampere Circuital law. At this point the current is a different at enclosed loop. At this point, at this point, at this point, at this point, at every point the current is different, which is flowing through that conductor. So that is gives here at an enclosed point the current is a different. So we'll calculate first that current. Now here inside the conductor, inside that conductor, R is less than of A, R is less than of A, and here the current is directly proportional to the area. Here the current is directly proportional to the area. The complete of that conductor, the current is directly proportional to the area. Area is pi A square. So I have taken here A, that's why. And for enclosed current, that is directly proportional to the pi R square. So equation 1 and equation 2 is there. So divide these equations, IE divided by I. Why? Because I want IE here. IE divided by I, and here if you taken, it means you can write these terms as like this: I equals to K, constant K, pi A square. Similarly here IE equals to constant K, pi R square. So if you divide it, then what you will get? You will get IE equals to I, then you will get R square divided by A square. So IE equals to the enclosed current is equals to the R square divided by A square into I. This times you will get the current. So now by using Ampere Circuital law, closed integral of B dot dl is equals to the mu naught into I. So already we know that, that is we can write this term as like this: integration, line integral of B into dl cos of 0 is equals to the mu naught into I. So then finally we can get this one. dl is nothing but 2 pi r, dl is nothing but 2 pi r, then B into 2 pi r is equals to the mu naught I. We can write that is, sorry, here we will get IE, IE for enclosed, IE equals to the I into R square divided by 2 pi A square, 2 pi A square. So sorry, here no, we will not get 2 pi A square, only A square. So and here 1 R and here 1 R is get cancelled. Then what you will get, the expression becomes mu naught into I into R divided by 2 pi A square. Here B is directly proportional to the I and R. B is directly proportional to the I and R inside the that conductor. the magnetic field inside the conductor is proportional to the distance. So then if you drawn a graph of outside the conductor and inside the conductor, then what you will get? You will get like this. So this is the magnetic field and this is the distance r. We will take distance r. So this is the distance r. We'll see first. So at 0 the magnetic field, the distance 0, the magnetic field is 0 now here. And if you increase the distance, then the magnetic field is also increases. Magnetic field is also increase as a linearly will take as a linearly at the point of A, at the distance of A up to here. And if you move away from this conductor, then what will happen? It is becomes reciprocal of that distance. So you will get in the decreasing order of that magnetic field. So this is the graphical representation of this term of magnetic field inside the conductor and outside the conductor. So let us take one assignment question. So write a statement of Ampere's circuital law and give the proof of Ampere circuital law. Thank you.